In this session we do our second formal proof, a proper actual proof, and it's as I was saying towards the end of at the end of the previous session, this proof, the theorem statement, is about the sum of the degrees of all the nodes in a graph, and the theorem statement says that that sum, that number, is even. Okay, that's the theorem statement, and you're asked to prove that. All right. So here's typically a theorem identifier, usually a number. Sometimes after the number will be a bracket, and then perhaps somebody's name. Joe Schmo's theorem. Trying to get a good example. Well, the name comes to mind. French mathematician Artin, A-R-T-I-N, and he has theorems labelled, named after him. So you could talk about Artin, A-R-T-I-N. So Artin's, possessive, Artin's theorem. So in a textbook you might have the theorem number, something like this, and then the theorem statement, usually a couple of lines, usually fairly short, and then after the theorem ID, usually a number. You might have round bracket, parentheses, and then some person's name, the discoverer of the person who created the proof. So like Artin, so A-R-T-I-N apostrophe S, Artin's theorem. Okay, so that would be sort of here. Here we haven't got it, but that's quite common. But there's usually always a theorem ID, usually just a number, so you can identify which theorem it is in the book or the article. So in some other theorem they may refer back to C theorem 27, and you might see that inside theorem 35 or something, so it's referring back to a previous theorem. So each theorem you need an ID, an identifier, so usually a number. And sometimes a theorem is so famous, proof, so famous that authors just use the name of the person. For example, Gödel's second incompleteness theorem, and no number, and it's just so famous. That happens as well. All right. So in this case, theorem ID, theorem statement. For any graph G, the sum of the degrees of all the nodes in the graph in G is an even number. Right? That's the statement. And then at the beginning of your proof, you just write out proof. That's very conventional. Right? So you know that the actual proof is starting here. Sometimes a colon or just a space. So proof. And here, end of proof symbol, your vertical, hollow, rectangle, right? End of proof sign. Alright, now that's pretty compact. Now a bit of thought has gone into it, of course. You try to be concise but complete. Now every edge, you make some statements, and then we'll make deductions, and then come to the punchline, so to speak. The final deduction that the theorem statement is actually true. In other words, even number. That would be your punchline. That's what we have to show. That number, the number you're talking about, is actually even. That's the point of the theorem. That it's actually an even number. All right. So here are your examples of statements, and then we make deductions from them, and then come to the final conclusion. So here are some initial statements, for example. And now every edge in G is connected to two nodes, right? By definition, that's what a node is, an edge is, right? like you have a node here and a node here and a line connecting them. That connecting line is an edge by definition. Okay, so every edge in your graph is connected to two nodes, right? And each edge contributes 1 to the degree of the node it connects to. Right? So here's an edge, and it's connected to that node, and it's connected to that node. Now there may be other nodes, right? Now each edge will add 1 to the degree of this node. It'll add 1 to the degree of this node. Okay? So each edge will increase the total of the degrees of all the nodes in the graph by 2. Right? So let's say I add another node, and then I connect. I make one more edge, so I connect this node to that node. Well, the degree of this node's gone up by 1. The degree of this node is 1. So the total number of degrees has gone up by 2 every time I add an edge. That's the essential idea. Okay. So each edge contributes 2 to the sum of the degrees of all the nodes. Right? That's what I'm saying here. Now, so that means now we're making a deduction, right? Now, so if G contains E edges, little e edges, well, that means that for each edge there will be 2 as your contribution to the sum of all the degrees, right? So if you have E edges, you'll have 2E degrees total. Okay? The 2 of any integer, 2 is an even number. I mean, 2 makes this an even number. 2e is an even number because of the presence of the 2. And this 2e is the total of the number of degrees of all the nodes in your graph. Okay? So it has to be even. And there it is. There has to be an even number. End of proof sum. Okay. So that's our second proof done. Now a whole new section. So chapter 0 and section 4, so 0.4, so you know where you are in the text. And the topic of this section is types of proof, methods of proof, various proof strategies. You can prove things in different ways. So, and some of them are quite famous. A proof method. You use this kind of proof rather than a different kind. So, or type, right? So types of proof. And the book mentions, talks towards the end of this chapter, we'll talk about 3 different kinds of proofs, of different types. One's called proof by construction, and we will do that this session, and then we'll run out of board. Next sessions, we'll talk about another kind of proof technique, a way of proving, a style of proving, if you like. Proof by contradiction. So you can probably guess what that's involved. You end up with a contradiction, and that helps you prove something. Okay, and the third one, proof by induction. If you've never done that before, it's probably a bit surprising. You've probably heard of it. At least most of you probably prove things by induction. But I won't explain that now. But it's a famous proof technique. So we've got 3 here that we'll mention. So we'll start with the first one. So just proof by construction. So what does that mean, sort of? Well, it means you're proving something by building something, by constructing something. Now that may seem a bit vague, so it's probably best to explain what that means by actually doing something, by actually giving you a concrete example of constructing something that you use. The construction, the thing that you build, provides the proof of your theorem, what you're trying to say. Okay? So, as a lead into this style of proving a theorem, following many theorems state that a particular kind of object exists. Like the statement will say, this type of object, mathematical quantity or whatever, exists. That it's possible that there can be this kind of object. That's a bit vague. I'll give you a concrete example now, and then for the next square, the final square, second half of this session, which is the last session of the board, we'll actually prove something of this type. That will prove that an object, some mathematical thing, some entity, actually exists. That it can exist. So we will prove its existence, that it does exist, that it can exist by actually building it, constructing it. So it's a proof, in this sense, proof of existence by actually constructing it, and then you can almost visually see that this thing, whatever it is, this object, mathematical object, does exist because you were successful in constructing it. You actually built it. I'm still being rather vague, but you'll see what I mean in a minute. Right? Now, before I get into the theorem statement and the proof, it's interesting. I don't see any end of proof mark. I'm not quite sure if I finished proving it or not. Anyway, but I need some preliminary stuff. You need like this be a definition. In fact, definitions is very important in pure math as well. We talked a bit about that earlier. Right? It's not just lemmas and proof statements and proofs and corollaries. Definitions also very important. And okay, so here's a definition. So a graph is said to be k-regular. That's the critical term. What does that mean? It means, so a graph is k-regular if every node has degree k.